It is it is now the top of the hour, and I want to thank everyone for registering and attending today's AVS eTalk webinar. Today's topic is going to be atomic layer etching of electronic and quantum materials for revolutionary solid-state technologies by Austin Minich from California Institute of Technology. And before I turn it over to him, I have just a few slides. First off, the question and answer and the chat features are two different options within Zoom. So please put your questions during the presentation into the Q&A feature and reference the slide numbers, and I will parse through them and we will have time for question and answer at the end of the presentation. For all other issues, please use the chat to talk directly to the AVS staff to resolve technical issues. We have several more professional development webinars, so please keep an eye out for them next week and next month. Here is another professional development webinar that you should absolutely check out, and there's a registration link here. Join our Thin Films Division LinkedIn group, scan the QR code, and join to see what we're posting. All things Thin Film Division and AVS, as well as the upcoming special topic collection, Call for Papers, and a reminder to get those in by November 1st. Speaking of November, I hope to see all of you guys in Pittsburgh at AVS 72. So we just opened the call for late breaking abstracts, so make sure you submit abstracts for that if you haven't already. They are due a little less than a month from now. And don't forget to join AVS. So with that, I will hand it over to Austin.
Okay, thank you. Let me get it going here. Does it look okay?
You're good.
Okay. All right. Yeah, thanks so much for the opportunity to the organizers. And I also want to thank the audience for taking time out of your day to listen in. I really appreciate it. And hopefully, I'll give you an interesting overview of our group's research into atomic layer etching. So first of all, kind of motivation for our group's work, I like to start with this image, which is a globally famous image at this time. It's the first ever image of a black hole. And you may know it was imaged not in optical wavelengths, but in the millimeter wave spectrum, which is about 240 gigahertz or so. And this was just a really neat image scientifically, but just as for the general public, a pretty neat image to see the center of the black hole there in that donut. And relevant to this talk is that we could not have gotten this image without thin film technology. So in particular, this image was acquired using a network of radio telescopes across the entire world that were stitched together to make a giant telescope using math. And inside each of these telescopes is a low noise transistor, which is based on these thin films that are grown with the highest perfection, essentially, of any material that people have figured out how to grow. So thin film technology is essential for our applications in daily life, but also scientifically to get these amazing images. All right, so we have now the image that looks like this. Now, wouldn't it be fantastic if we could get an image that looks like the one on the right? The right one, unfortunately, is not an image we've acquired experimentally yet. This is a simulation of what one could obtain if we had, for instance, radio observatories in space so that we could get better angular resolution of the image. Well, what I hope to convince you is that we really need fundamental advances in thin film science and technology, like those transistors I described before, to achieve this vision. And so that motivates our group's research into a few topics, and then more broadly, it's solid-state technologies, for instance, this lithium niobate quantum photonic integrated circuit, all of these technologies, we really need ways to deposit, process, etch materials with atomic scale precision. And so that's what I'm going to talk about today. The first two topics are atomic layer etching of superconducting niobium nitride and lithium niobate. And then, although the talk title is atomic layer etching, we have some very recent results on thermal laser evaporation of superconducting niobium films, which I wanted to present, and I think it'll give a nice variety to the talk to finish things up. All right, so first, atomic layer etching of superconducting niobium nitride films. So first of all, metal nitrides are widely used in the superconducting world and technology, for instance, for qubits, as you see in this image, as well as for various detectors like this microwave kinetic inductance detector, which can detect single photons as well as their energy. And that ability makes it the leading technology candidate for studying exoplanet atmospheres by allowing spectroscopy on those single photons. All right, so metal nitrides are a really key material platform for superconducting devices due to these properties that you see on the slide. However, there are imperfections in these films that presently limit the sensitivity or other performance metrics of those technologies. So for example, that kinetic inductance detector I showed you is basically a microwave resonator, and the photon changes the resonance like what you see here, where there's a dip at a certain frequency and the photon kind of shifts that around. But unfortunately, intrinsically, it's experimentally found that there's a jitter in this frequency even without any photons, and that has been traced to imperfections in the film surfaces. If you're more kind of expert in this area, these are called two-level systems in the film surfaces. Similarly, this is a plot of quality factor versus temperature. The red line is what you would expect from BCS or superconductivity theory, where the Q increases essentially to very large numbers below a few hundred millikelvin. But what's actually observed is this plateau of the Q, which again is attributed to these imperfections in the surfaces. So these two observations motivate the need to engineer surface microwave properties, but very, very delicately on the atomic scale so that we only modify the surface without disrupting the bulk of the film. All right, so that is the challenge. With continuous etching, only modifying the surface with low damage is very difficult because you have energetic ions, which impart damage even several nanometers below the surface. And in addition, it's quite hard to control the amount that you etch because it's a continuous etching process where the amount is controlled really by timing and calibration. In contrast, atomic layer etching takes the individual steps in the continuous process and separates them into sequential and self-limiting steps. So what that means is that, say we start in the center of the slide with the yellow circles that modify the surface, and the process is selected such that those yellow circles only modify the top layer of the material, and then the reaction stops. Then we remove the yellow circles and we introduce the light blue circles in the right image, and that reaction is also designed to only react with the yellow. And then once that yellow modified region is gone, the etching process stops. And so this is the way we can get atomic monolayer scale control over etching. And if this sounds familiar, for example, for atomic layer deposition, it is very analogous to atomic layer deposition, but here material is removed rather than deposited. So ALE is a potentially transformational technique in nanofabrication for this solid-state technology, because you automatically get Angstrom-scale etch control, which provides the fine ability to manipulate surfaces. And in addition, in many cases, it exhibits a surface smoothing effect to sub-nanometer scales, which is well below what could be achieved with existing techniques. All right, so let's get into the results of this first part. Previously, we developed an ALE process for titanium nitride, and it consisted of a modification step with oxygen gas to oxidize the top surface of titanium nitride. We then used a plasma mixture, which we call in situ HF. It consists of SF6 and H2 plasma, and this was found to selectively etch the oxide, but not the nitride. This is a plot of etch rate versus the ratio of those two gases on the x-axis. And you can see when titanium nitride in blue has the titanium in the 3+ oxidation state, there's no etching because that fluoride product is not volatile. But in the titanium dioxide case, where titanium is in the 4+ oxidation state, we observe etching due to the formation of TiF4. So this was a good finding, and the goal was to adapt this to niobium nitride because niobium nitride is actually used widely in addition to titanium nitride owing to its higher transition temperature. So as a first step, we applied the same process to niobium nitride. Unfortunately, what we found was not ideal. So here's a plot of the change in thickness versus number of cycles. And we see that although there is an initial etching at the beginning of the process, the etch rate eventually plateaus after about a nanometer of removal. This is, of course, not desirable because we'd like to be able to run this process as many cycles as we like. Now, in retrospect, this is not so surprising because niobium is well known to have diverse oxidation states, and only one of them produces a volatile fluoride, that being Nb2O5. It's been actually studied in the superconducting community. What are the various oxides that are formed on the surface of a niobium film? And this is a bit of a complicated plot, but you can only focus on a few things to make it easier. Just look at the green region in each of the plots, starting from the right. The green region is the phase that we want, and you can see it forms more readily at lower temperature, 293 Kelvin, whereas when you go from right to left at higher temperature, the surface becomes more of these lower oxidation state oxides like NbO2 and NbO going into the depth of the film. So it's clear that the issue that we were having is that we were oxidizing at too high of a temperature, which yielded the wrong oxide. As a test of that hypothesis, we did a very manually intensive process where we performed the fluorination at a high temperature in the reactor, but then we took it out into the load lock and oxidized it at room temperature. And this is rather painful to do, but it at least helps us validate the hypothesis. And indeed, we see now a thickness change that doesn't terminate after 20 cycles. So this is good for confirming the hypothesis, but it's not very practical because it's very intensive manually and it's quite slow, 10 minutes per cycle. But with this understanding, we can figure out what we need to do to change the process. And the way to do it is to change the oxidant. So this is an XPS plot where it's intensity on the y-axis versus the binding energy on the x-axis. And this is niobium 3D peak after exposing it to oxygen gas. And you can take the experimentally measured peak and decompose it into the subpeaks, which are attributed to particular types of bonding with niobium. And from that, you can compute the fraction of these bonds that are associated with Nb2O5. And that turns out to be 41% in this case. Now, to get that higher, we can use a stronger oxidant, which tends to lead to higher oxidation state oxides. And a straightforward way to do that is using oxygen plasma exposures. And so when you do this and do the same characterization process, you see that the Nb2O5 fraction is now much greater at 75%. And so this gives us hope that with this different oxidant, we can achieve etching that is not terminating. All right, so here's the experiment to see if that works. This is etch rate versus the flow rate ratio, like I showed earlier for titanium nitride. This is now for niobium nitride. And you can see for the ratios that are shown, there's very little etching of niobium nitride, up to about 0.3 ratio. Now what we hope is that there's some window where the oxide does etch. And indeed we see that in the range of about 0.2 to 0.3 or so, there is that same window where the oxide etches but the nitride doesn't. Okay, so we have successfully found the selective region now for niobium nitride. For the rest of the results, we used the value of 0.3 ratio just to make the etch rate higher. Okay, so this gives us now an ALE process for niobium nitride. A key test for ALE is when you apply each half step independently, you should not observe any etching, but when you apply them both together, you see etching. And this is usually plotted as this change in thickness versus number of cycles plot. So you can see here, when we do one step, we see no etching. When we do the fluorination step, we also see no etching. But when we do them both together, we see etching. In particular, it does not terminate like we saw before. Okay, there's lots of characterization that can be done, which are, if you're interested, that's in the paper. I'm just going to finish this part by reporting the electrical characteristics of these films. One nice thing about niobium nitride and other superconducting films is that the superconducting transition temperature is very sensitive to the material quality. So we measured that for niobium nitride. This is a plot of resistivity versus temperature. The original film was 30 nanometers, and it had a transition temperature of 11.22 Kelvin. Now, as a reference sample, we etched a sample with reactive ion etching. And that's this sample here. Its TC was 10.5 Kelvin. It's 22 nanometers. And it's known that the TC of these films depends on the thickness, and the lesser the thickness, the lower the temperature. So it's not surprising that this reactive ion etched film has a lower TC. But now what we can do is compare this TC to that of the ALE etched film, which has a very similar thickness. And interestingly, we see that although the ALE film is just slightly thinner, its TC is actually noticeably experimentally larger than that of the RIE etched film. And this highlights the low damage nature of the niobium nitride ALE process. The fact that even a slightly thinner film has a higher TC. So this is showing that we've made some progress towards the goal of modifying just the surface region while minimally affecting the bulk of the film. Okay, so what we would do in the future to apply this process is essentially to start with a uniform niobium nitride film, and we do all the fabrication as normal. We'd end up with that third panel there with a device with some imperfections and surface oxide, and then we'd apply this, so I should say niobium nitride ALE to achieve the final device. If you're familiar with superconducting device characterization, this is a challenging measurement, which is for us been a challenge to actually do it, but others have kind of taken note of our approach, and Amazon, the quantum effort there, has applied this approach to aluminum qubits, and they've observed about a factor of 2 enhancement in the lifetime of those devices. And that, if you're interested to follow that work, that's available in the link. Okay. So now moving on to atomic layer etching of lithium niobate. As I showed in the beginning of the talk, lithium niobate is a very interesting material for nonlinear optics on chip as well as quantum information processing. And the reason is that lithium niobate has lots of properties that you'd like in a quantum integrated circuit, all in one material. So in particular, it has a wide transparency window and optical nonlinearities. The challenge is that it's very difficult to process. So if you look on the left here, there really isn't a great way to etch it in a dry etch chemically. And so what's used is ion milling. But this ion milling produces redeposition, which coats the sidewalls. So you can see all that gunk on the real lithium niobate sidewall in the left image. So this material has to be removed, otherwise the optical characteristics of the devices are terrible. You do that with a wet etching, and there's some very interesting chemistry, which is very frustrating for device folks, which occurs. For the chemists, this is great, but for the device people, it's very frustrating, which is on the right. The wet etching actually etches the different ferroelectric domains of lithium niobate at slightly different rates. So the different arrows there you see are different domains, and you can see circled in red the corrugations formed by the differential etch rate of the different domains. And that feature that you see in those red circles is the dominant loss mechanism at present in lithium niobate devices. So kind of no matter how you go about it with the different techniques, processing lithium niobate is a challenge. All right, so what we really want in this pattern transfer process is, if we look at this side view of a waveguide, there's a few parameters you can see here that are relevant, like sidewall angle. What we need is near vertical and atomically smooth sidewalls. And in addition, the etch depth precision is extremely important for the nonlinear processes occurring in these chips. Presently, with ion milling, maybe 20 nanometers precision is achievable, but we would really like plus or minus 1 nanometer, which corresponds in a relative sense to 0.1% or so of the etch depth. That's extremely challenging to achieve with a continuous process. All right, so that motivates the need for ALE of lithium niobate. The first approach I'm going to talk about is motivated by something that's known in the lithium niobate field for a long time, which is it's called proton exchange. And the idea is that the challenge with lithium niobate etching is the formation of involatile salts like lithium fluoride. With proton exchange, you essentially put your chip in acid and let the hydrogen replace the lithium on the crystal lattice. And then you have a surface that's depleted in lithium, and you go from this type of picture, which you can see all this horrible looking micromasking and so on. You go to something more like this, where you can see you get a very vertical sidewall, and it's definitely smoother, although certainly not perfect. So this was our motivation to pursue an atomic layer etch process where hydrogen plasma kind of takes the place of this wet step. All right, so here's what happens when you expose lithium niobate to hydrogen plasma. So this is an optical image where the photoresist has been removed, and the dark spots are the regions where the sample was exposed to hydrogen plasma. And you can see that the optical properties have changed very markedly because they're dark rather than transparent as lithium niobate is at the optical wavelengths. Now, the other very interesting thing is that when you then expose this wafer to SF6 argon plasma, it very, very selectively etches the darkened regions over the unmodified region with a selectivity of something like 99%. And this is an AFM scan where the lower parts of the scan correspond to the dark regions in the left image. So this is very interesting, and it means that's the ALE process right there because it's so selective. You do H2 plasma, and then you alternate with SF6 argon plasma. Here's the familiar plot I showed before. This is thickness change versus number of cycles. When you only do H2 plasma, you basically don't see much happening for etching. When you do SF6 argon, again, you see very little thickness change. But when you do both of them together, then you get about 1.6 or so nanometers per cycle. We are interested in the mechanism behind this etch selectivity. So a collaborator helped us to do reflection, high energy electron diffraction, or RED, characterization of the surface. So the left image here is the original as received lithium niobate, and you can see the peaks and rings that are associated with good crystalline order at the surface, producing peaks or streaks for a 2D truncated surface. On the other hand, after you expose lithium niobate to hydrogen plasma, those features largely disappear. If you really look carefully, you can see still there are some rings, but which would indicate a polycrystalline character of the surface, but clearly the surface has been markedly disrupted. And so the hypothesis is that that disruption facilitates chemical reaction with the SF6 plasma, the fluorine radicals, that then produces etching. So this is the current theory that we believe is the origin of the selectivity. Okay, so we'd like to have this process improve device performance somehow. And for optical devices, the way that would happen is by smoothing the sidewalls so that you get fewer scattering losses. So this is an AFM scan of a state-of-art waveguide sidewall. If you're curious how we got this, because it's a sidewall, the answer is that the sidewall angle is relatively shallow at about 65 degrees. And that's, of course, bad for the device, but it makes the AFM characterization a little easier. And so the roughness here is about 0.8 nanometers RQ. After the process of 50 cycles, we can see the roughness has decreased to about 0.55 nanometer. So that is a promising indication that this sidewall smoothing from the process can decrease scattering losses in thin film lithium niobate, or TFLN as it's called. All right, so the second part of this section on lithium niobate, I want to discuss our subsequent study where we're trying to improve some characteristics of the previous etch. So the two limitations of that previous one I just showed are that redeposition still happens because of lithium fluoride, and in addition, it's not directional. So it's not really suitable for pattern transfer. So we decided to improve those characteristics by using heavier halides, particularly bromine plasma, which according to this boiling point versus halide type plot should yield higher vapor pressure products. Because you see the bromine products have a lower boiling point, and so they should have a higher vapor pressure at a given condition. Therefore, there should be less redeposition. In addition, we changed the process so that there's a directional argon plasma step as the removal, which is at the bottom right of the slide there. So with that, we have a proposed new process, which is HBr BCl3 argon plasma, and then that's a modification, and then the argon is plus ion step is the removal. There's a lot of characterization that we did that I don't have time to fully go into, and it's all available in the paper if you're interested. But the one point I did want to highlight is the benefit of using ALE for even for pattern transfer, which could be etches 200, 300, even 500 nanometers deep. One challenge with the existing approach for lithium niobate, which uses ion milling, is called aspect ratio dependent etching, ARDE. The origin of this is, if you look at the right of this image from the work cited, that when the gaps get narrow, meaning higher aspect ratio, there's less ion flux to the bottom of the trench. And since the material removal rate is proportional to the ion flux, that means there's less etching at the bottom of the trench. And you can clearly see that on the right of the image there, like the 100 nanometer gap, it's essentially not etched because of this effect. Now, ALE is less susceptible to that because the amount that's etched is actually not proportional to the flux anymore, because we can just wait as long as we need to for that modified surface to get removed. And that leads to this observation where we can produce aspect ratios that are essentially not achievable with ion milling in lithium niobate. So this is an SEM image we acquired of our processes, the process that I just showed using bromine plasma. And you can see we can get 150 nanometer gaps in lithium niobate, whereas it's not possible with ion milling. Okay, so similarly, now the difference between this case with lithium niobate and the niobium nitride superconducting devices is that optical characterization is not easy, but certainly much more straightforward than for the millikelvin temperature cryogenic characterization for the superconducting case. So this is a characterization that we can indeed do with our collaborators at Caltech, and we have the setup shown here. We can make these micro disc resonators shown at the upper right, and we measure these and we get Qs of a few million, which is pretty good. And so then we can apply this process, which yields sidewall smoothing, and observe the effect on the Q. And this can be a way for us to demonstrate that the process leads to actual device improvements. Okay, so just getting to the last part of the talk. Now, as I mentioned at the beginning, I'm going to switch gears, and it's not going to be etching anymore. We're going to be talking about deposition. And this is thermal laser evaporation of superconducting niobium films. Okay, so PVD techniques, physical vapor deposition, are really important in semiconductor industry as well as the quantum industry, because materials like niobium and so on, tantalum, are of great interest for qubits owing to their, niobium in particular, superconducting characteristics. So it's very important to be able to deposit them with very high quality. The challenge, though, is that the materials, like I've shown here, are very refractory, meaning you have to heat them to really high temperatures to get good vapor pressure for deposition. And that leads to a lot of difficulties with physical vapor deposition. So for instance, you can just use resistive heating within a fusion cell, but these can only get so hot, and it's quite difficult to deposit these elements. In fact, it's really not possible for the elements shown, because the temperatures are too high. Electron beam evaporation is standard, and it's been used for a very long time, but it's still difficult to deposit certain elements because of temperature limitations, although you can just with a slow rate. And in addition, co-evaporation is just practically challenging, although it can be done. There's a lot of practical challenges that make it difficult to use this technique in certain applications. So the alternative is to use non-thermal techniques, for instance, like sputtering. This is widely used, and of course, it can certainly deposit many films, but there are film damage issues from the ions, the fact that there's a plasma in the reactor, and some compounds can be difficult to sputter. PLD, pulse laser deposition, is another technique, but it has its own complications. So like everything in life, nothing's perfect. All of these have their strengths and limitations. But what if you could go a thermal route and avoid some of the complexities of these non-equilibrium techniques, but produce vapor from any element? That's the idea of thermal laser evaporation. And this technique, a continuous wave laser, not a pulse laser, continuous wave laser, is focused onto a pellet of material. And you can see in the center right of the slide in that little box, that creates a locally hot region, a melt pool potentially, contained within the overall pellet. And because lasers are now available with kilowatt scale powers for a relatively inexpensive cost, you can focus this light onto essentially any element and get vapor from it for deposition. So there's a lot of advantages for TLE versus the other techniques I showed. In particular, you can evaporate essentially any element, and this has been demonstrated. You can deposit at higher deposition pressures because the laser light is only weakly interacting with any background gas in your chamber. And very importantly, there's no crucible needed because the material itself is its own crucible. And that's really enabled by the ability to focus light much more easily than electron beams. Now, there's a group in Max Planck which has made a lot of progress in the modern incarnation of this technique. There's now a company that they've spun out called EpiRay, which is selling these. At the time that we started this work, this wasn't really available, and so we essentially built our own setup, which I'll show in a second. But our overall goal with this is to be able to deposit high-quality thin films with refractory elements, and really with properties that you just can't achieve with the existing PVD techniques. Okay, so here's our system. I want to mention how amazing it was to me that there's a lot of new stuff here, but a lot of this is eBay parts, thanks to the semiconductor industry, having all their old stuff on eBay. So you can really do a lot with what's available out there secondhand. These fiber lasers are new, though. Those are kilowatt scale lasers outputting to a fiber. This is the beam delivery system, which gets the beam into the chamber. We also have substrate laser heating using a CO2 laser for heating the growth substrate. This is a target holder and the substrate holder. Inside, it looks like this. Our system is designed for centimeter scale chips, owing to the substrate laser heating approach. The yellow line is the target heating laser, and the target you can see at the bottom of the image there. Okay, so the first thing I'm going to show is our deposition of nickel. Nickel was chosen because it's a bit easier of a material to deposit. It has a lower melting point than niobium, for example. And there's a lot of data on electrical conductivity of thin films, so we can figure out how well we did. Okay, so we deposited onto sapphire. For this case, we used 180 watts of 1070 nanometer power, continuous wave. That was focused to about 800 microns on the pellet. You can see afterwards that we melted that region so that we definitely did something. We deposited 14.7 nanometers at about a third of an angstrom per second. And that's a pretty typical value for evaporative techniques. Okay, so just some kind of sanity checks. The deposition rate should follow an Arrhenius relation with temperature. It's not so easy to measure temperature at the target surface, so what has been done in the field is you just assume the growth rate is proportional to the vapor pressure and therefore also follows an Arrhenius relation with an empirical constant. So this is a plot of deposition rate versus inverse power, and the SMART 2023 is a previous work from the Max Planck group. Our work is shown here. There are some reasons that the slope is different, which are discussed in the paper, but you can see it's still following the expected Arrhenius relation, which is reassuring. Okay, so we measured the surface roughness as a first characterization. The film was 14.7 nanometers thick. The RQ is 1.1 nanometer, and this is expected for kind of nucleation and coalescence type growth of a metallic thin film. This is comparable to what others have reported. With XPS, this is XPS of the surface. Unsurprisingly, there's a native oxide, so you can see the orange lines are oxide, the blue lines are nickel, and then there's an adventitious carbon peak in purple. To kind of get the bulk properties a little bit better, we did depth profiling XPS, and then we did the analysis. So this is composition versus milling time into the depth of the sample. And the kind of light gray shaded region is the bulk before we get to the substrate on the right side of that plot. And you can see it's mostly 90-ish% nickel with some degree of carbon and oxygen. The exact origin of that is not totally clear, but that's what we find. But in terms of resistivity, it's quite good and comparable to previous studies. So the red is our result, and the other data are resistivity versus film thickness. So this is indicating we're getting pretty good quality nickel films compared to what has been reported. But now I want to go on to niobium, because we don't need TLE to deposit nickel. What we do need, though, is we need TLE for niobium, or at least it's quite helpful to have it. Its melting point is 2750 Kelvin, and in addition, its critical temperature for superconductivity is very sensitive to material quality. So this will be a very good test of our setup. So compared to before, everything looks basically the same, except we need a lot more power, and we have to focus the beam more tightly. So when you consider the power density owing to the decreased diameter of the beam and the increased power, it's at least a factor of 10 to 20 higher power density on the target. And again, we confirmed that we did something by looking at the surface afterwards, and clearly it was melted. And in this case, we deposited at 0.2 angstroms per second. All right, so I'm going to go a little bit faster through this just to make sure there's time for questions. But we did X-ray reflectivity. We got about 25.7 nanometers. The roughness comparison is quite interesting. So it's very low roughness for TLE, and you can see on the right a sputtered sample in our clean room here, and it's quite a bit rougher. The sputtered one is. We did some characterization via XRD, and we find, although we should expect if it's epitaxial on C-plane sapphire, we should only see the 1 bar 1 1. We also see 110, as you can see in the left image. And so this is not surprising. This is indicating this is a polycrystalline film with different orientations. If we look at the 222 peak, we can analyze the width, and we get a grain size of about 6 nanometers. Okay, so the last thing I'm going to show here is I think the most interesting. This is the superconducting properties of this film. This is resistivity versus temperature. Its room temperature resistivity is shown. A common metric in the superconducting field is the triple R, which is the residual resistivity ratio. We just divide the resistivity at room temperature by that at 10 Kelvin. And typical values of this are maybe 2 to 3. If you have epitaxial niobium, it could be 30 to 100. So we're getting 5 to 6-ish, which it's pretty good considering its unheated growth. It's about a factor of 1.5 to 2-ish more resistive than bulk, thick lithium, or thick niobium rather, which is also pretty comparable. But the interesting thing is the TC. This is resistivity versus temperature zoomed in around the transition temperature. Its TC is 9.23 Kelvin, and the width of that transition is only 40 millikelvin, which is quite competitive with what's reported. And it's in particular, the TC that we measure is only 20 millikelvin less than the bulk, despite the fact that this is a 20 nanometer thick film. So this is indicating a very good quality of this niobium. Just for reference, we've sputtered films, as I showed before, and for those films, we get maybe 7 to 8 Kelvin of the TC value for those films of a similar thickness. Okay, so that's showing the approach and ability of the system at this moment. What we really want to do now is grow some interesting materials that would be very challenging to grow with any other technique. In particular, we have the ability with 2 lasers to co-evaporate and form binary alloys. We can grow ternaries by introducing, for instance, nitrogen plasma as the third component of the ternary alloy. And with this, we can grow lots of interesting, for instance, ceramics, refractory nitrides, carbides, borides, and other materials. All right, so just to sum up, our lab is really motivated by this kind of vision where we can go from the image on the left to this image on the right and do some really interesting science, as well as just make people excited about this kind of physics and science. But I hope I've convinced you that to do this, we really need thin films, science and technology. And so that's what we are really aiming to do. All right, just really quick, I want to thank very much the students who have really been brave to take eBay parts and put it all together and figure out how to make the system do something. It's really difficult to do that, and I really am grateful to them. The work I showed was done by the students. You can see at the top. We have the collaborators shown, and then I also want to acknowledge the funding sources that make this work possible. So with that, thank you so much for attending and listening, and I'm happy to answer questions.
What a fantastic talk. Thank you so much.
Thank you.
So, so there's quite a few questions, so I'm going to go ahead and dig in. Um, One of the questions that got asked and is now being answered live in the chat is, so for these defect-sensitive materials, how much of a problem is the diffusion into the surface? So that was a question I had as well, as far as like, especially with like oxygen plasma. Are you worried at all about the oxygen diffusing into like the niobium nitride layer?
Yeah, that it's a very good point. It can happen. Particularly oxygen can diffuse along grain boundaries and get quite deep into the film. But even if that's not what's occurring, there's residual fluorine, for example, in the film surface. I think the best answer for that is the Amazon team did a study where that all those processes certainly could happen, but despite that, they found improvement in lifetimes by pretty decent factors. So clearly those processes happen. Whether they're important for the given metric, it definitely depends on the circumstance.
Absolutely. Yeah, that's a great answer, and I appreciate it. Um, Moving on. So this was specifically at the beginning of the talk on slide 7 regarding the
Okay.
saturation of the quality factor below 200 millikelvin due to the TLS dissipation. What specific atomic scale treatments or passivation have been proven, or do you think is going to be most effective in preventing this saturation?
Yes, so that saturation is attributed to surface loss. And the surface loss arises from two-level systems in the oxide or other imperfections in the surface. For aluminum, as an example, that oxide thickness could be 30 to 50 angstroms thick, right? It's pretty thick.
Mhm.
And so there's a notion of a volume giving a certain number overall of TLS, which then manifests as a certain loss. So if you just decrease the volume of that oxide, without being anything super complicated, you just decrease the total number of TLS, and therefore you decrease the overall loss of your superconducting device. So it's really as simple as that, the argument. You're just decreasing the volume of this lossy surface material.
That makes sense. Thank you again. So another question that I had as well while you were talking, do you ever worry about damage on the surface from the plasmas, whether you're talking about O2 or the SF6H2? Especially you cited the Amazon work, which is extremely interesting, and I believe those were all thermal processes. So,
Yeah, that's a good point. It is something that we worry about. It depends on the material though. With lithium niobate, you kind of can't do anything at least for now, right? Maybe there is some chemistry, but at the moment you need plasma. So these oxides, which are super stable and resistant to any chemistry, they're you have no choice. But whether the optical loss of the surface after, that is an active research question. But we are optimistic that something will come out that is, despite that issue of the damage from the plasma, it will be okay. I should also mention that people might be thinking of plasma damage in the context of RIE, but here with ALE, the bias and all the parameters are much milder compared to what people might think about for RIE, so that degree of damage is lesser.
that's a great point. So this is a fun question. Do you think that the thermal laser evaporation can be used in production? Do you think that this is a scalable technology? Oh,
Yeah,
it's right there.
that's something we think a lot about. It depends which industry you're in, I would say. Fundamentally, point source methods have a challenge compared to like sputtering, where you can do 12 inches very easily, right? Having said that, there are ways you could certainly imagine that you could engineer your way out of that if you needed to. But I think certainly it's an easier case if you start with a lower volume industry where despite it being a point source, the wafer, for instance, flow, you don't really care if it's slow. In addition, the quantum industry, nobody has a personal quantum computer right now, so it's not really an issue for in terms of that nature of scaling.
Absolutely. So for the ALE, what type of plasma are you using? Inductively coupled, capacitively coupled, etc.
Yes, they're all inductively coupled plasmas.
And then are you using a like commercial ALE setup or is this all home built as well?
The all the ALE works I showed were done with Oxford Instruments tools. Yeah,
That
so
makes sense.
Flexol and Cobra.
And then for your niobium nitride that you were etching, did you deposit that using PVD or ALD?
We there is a mix of samples. So some were sputtered actually at JPL. Others we have deposited it via ALD in that same tool before.
That
And
makes sense.
you can actually you can get pretty good nitride and niobium nitride by ALD in terms of its TC value. Um, it's actually pretty good. You might think you're leaving all this precursor gunk behind, which you probably are, right? Few percent. But despite that, it actually, in the sense of TC, it's pretty good. By pretty good, I mean like nitride, maybe the best you can get is 4.5 Kelvin, and with ALD, you can get 4 Kelvin. So it's pretty good.
Fantastic. Let's see. Have you noticed any difference in the native oxide layer formation of your thermal laser evaporation, your TLE deposited niobium layers? Difference as far as like, do you think or have you measured thicker native oxide or any differences there?
I would have to talk to the students to see. We didn't, that's not, well, we did ellipsometry, but we did not focus on that oxide thickness so carefully. My prediction is it wouldn't be very different, but
That
I
makes
have to get
sense.
checked. Yeah, yeah.
See. So this was one of the pre-submitted questions. Are you aware of ALE being used already in production, like in high volume, uh, computer chips or anything like that?
Yes, talking to folks at the various meetings, I think it is being used. Although I'm probably not the best person to ask because I just hear the rumors. But yeah, my understanding is it is being used because actually it's mainly because of selectivity enhancement. Over between silicon nitride, silicon oxide, and silicon. That's the main reason. It's used in kind of a quasi ALE manner rather than maybe true ALE. But yes, I think it's used now, and as well as in nitrides. I think it's again a selectivity argument between the different alloys of gallium nitride.
Fantastic. Yeah, I hear those same rumors, so
Yeah,
I would agree.
yeah.
Um, and so this one for ALE, the question that was asked is, do you have any control over etch directionality? And I also want to kind of piggyback on that of you were talking about the differences in the etch of different lithium niobates. Have you ever considered kind of leveraging that kind of like facet selectivity or like say termination selectivity in
Hmm.
etching.
Yeah. So the directionality, like it depends on the process. Some cases there just isn't a way to get it, but in like the lithium niobate HBr process I showed, there you can just in the ordinary way you do with RIE, right? You can tune the ion angle distribution to make it more or less isotropic. So you certainly that it's the same concept here. Um, Yes, and regarding lithium niobate, in principle, you could get facet selectivity. I think I haven't thought about it. The issue is that the device folks have kind of converged on a particular material, meaning it's like magnesium oxide doped. It has a particular crystalline orientation. There's all these requirements from the device side, which means that um, you maybe you could get etching of different facets, but it wouldn't be that applicable to the actual scenario that you have.
Yeah, that makes total sense. Um, so another question, and I'm going to piggyback off this one too. What is the ion energy of the argon ions in the removal step of this was for slide 27 process? And then what I'm going to piggyback is you called it directional argon ions, and I was wondering if you bias the stage or what makes the argon ions directional.
Yes, the argon energy. I I'm a slightly fuzzy, but I want to say kind of tens of eV, something like that is my recollection. This is the self bias plus the DC or the I mean the stage bias. The stage
Stage
bias is
bias.
order of like a few watts or something. It's
Okay.
not huge, but there is a stage bias.
And are you doing that in sync with the cycles, or is it just throughout the whole
I think it's
process?
always on, although the effect of it is not totally clear. I think for experimental simplicity, we just leave it on. Yeah.
No, that makes total sense. Um, let's see. So this was an interesting question. And maybe you can comment on this, is this was submitted ahead of time. What are some options or approaches to recover the surface chemistry to the pre-ALE state after the ALE process? So,
Hmm. Yeah, it's a material specific question, I would say. So something I didn't present, but which we have an ongoing study is for silicon quantum devices, nanomechanical devices. There, we're etching, and the nature of the process is such that the modified part is removed, and you just end up with silicon again, right? That's the best case. You can't hope for that in most cases. So the various options are like for lithium niobate, you could apply our process to smooth the sidewall. Then you could do a short RCA dip to essentially remove whatever gunk is left over. And then you'll arrive at the same surface in terms of composition you had originally, but it'll be smoother. So there's strategies like that.
yeah, that makes total sense. And with that, I think I'm gonna ask everyone to thank Austin again for the fantastic talk, and I'm going to try to share the um, intro slides one more time to just remind everybody to sign up for the upcoming webinars, including blah, blah, including mentoring up, ways to get what you need from your mentor next week, and using expectations documents as a tool to improve your mentoring relationships next month, as well as beyond the checkbox, evaluating peer review through structured evaluation. Also coming up next month, join the Thin Films Division LinkedIn group, submit to JVST Special Collection. AVS 72, come see me. This is going to be a fantastic conference. And let's all thank Austin one more time and have a really fantastic day. Thank you guys so much for your questions and thank you for attending.
Yeah, thank you to the organizers and thanks everyone for attending. Appreciate it.
Thank you both. Have a good day, everyone.
So Jessica, I'll hop off, but yeah, I appreciate it. Thank you. Yeah,
Thank you so much. This was
yeah,
amazing.
yeah. Thank you. Hope everybody got something out of it. Yeah, yeah. Okay, I'll see you next time.
Don't know how to end. Haha.